So what I thought we'd do today is, first of all, I thought we'd just go through the field of view part of Tuesday's lab, which is, one of the two problems that we have to solve on Tuesday. And then next of all, we'll kind of move things along a little bit by looking at some of the equations of motion and how we can use basically Newtonian physics to make things move more smoothly in Unity. So the first problem then, was the field of view calculation. Just a quick show of hands, how many people got the field of view bit working? If you didn't get it working, no problem, we'll do that. How many people got the path following working? Excellent. Right, so I won't spend too long on the path following. I'll just really quickly show you the path following code that I made. And then afterwards, let's see. Yeah, then we'll talk about the field of view, which is like the other, and there's another interesting calculation as well, right? So the path following is pretty straightforward. I'll just zoom in and show you how that one worked for me. So this is my guard code, right? So first of all, I have, you guys, I'm not going to spend any more than a minute or two on this because if everybody solves it, there's no point, right? So here is my start method. So I just have a Boolean flag called random path. Because I made the waypoints a public field, I can actually add waypoints through the Unity editor if I wanted to, or I can add my waypoints randomly in the start method like this. So this Boolean flag is set to be true, but we'll go and add random waypoints. So the 0th waypoint that gets added is the object's starting position. So that means the object will start from its starting position. That's waypoint number 0. And then I go and add 9 more waypoints. To generate the waypoints, I just use random.InsideUnitSphere, which will give me a waypoint which is obviously inside the unit sphere. In other words, the distance from the origin to the point is going to be 1. Okay, and that just clamps it. Okay, and then I multiply by the radius that I'm looking for. So if it's inside the unit sphere and its radius is 1, and I multiply it by the radius, its radius is now going to be radius. Okay, it's not quite right because then when I set waypoint.y to 0, that's going to change the radius, of course, isn't it? Because what I'm actually doing is taking it up here and this distance, but then what I do is instead of actually rotating it around so that it's on the plane, all I do is clamp its y value to 0, so it just dropped it straight down onto the y-axis. So it's no longer going to be a radius anymore, but it's not too important, okay? So then I add waypoints, okay? So there's my waypoint setup. For the waypoint drawing, I have my method onDrawGizmos, and for onDraw gizmos, every time I'm drawing a line, I need 2 points. I need a current point, I need the x1, y1, and I need the x2, y2 point. So in order to generate that, I start my for loop at 1 and go up as far as waypoints.count. And I go I is less than or equals to, so which means I'm going to go 1 element too many. You know what I mean? Because normally I would go for I equals 1, I is less than waypoints.count. If I go less than or equals to waypoints.count, then that means it takes 1 element too many from the array, and if I didn't do something like get an array index out of bounds exception, because when I try and read, if my array of waypoints, or my array list of waypoints had, let's say, 10 waypoints, the last waypoint is going to be 9, so normally you go I is less than waypoints.count. So I'm going to go 1 element too many here, okay?
Why do you have I set to 1?
Because what I want to do is my waypoints are set up, if I want to do my waypoints like this, we'll say here's my waypoints, right? I want to go 0 to 1. Line number 1 is going to be 0 to 1, and then line number 2 is going to be 1 to 2.
Oh, so I equals to 0 will give the origin as opposed to the first waypoint?
Not necessarily. No. It will give the first waypoint. It will. If I use 0, it will give the first waypoint. But if you look at how I generate the waypoints, the very first thing I do is I take the previous one is equals to waypoints at I minus 1. If I was to start I at 0, I minus 1 would be minus 1, and I'd get an array index with a bounds exception. So I start at 1, and then I can go I minus 1 to get the 0th one, and then I can go waypoints at position I to get the current one. So there's one little sort of tricky hack that I used here as well. I used the modulus operator here. So I go next equals waypoints at position I percentage or modulus waypoints.count. Okay, so modulus, if you remember, is a way of clamping a number between a certain range. So if I had 10 waypoints, right? And I was 10. If I take 10 percentage 10, what do I get? 10 modulus 10 would be 0. So this is a way of saying if I'm at the last one, use waypoint 0 instead of waypoint number 10. So it's just a little kind of a tricky hack. And that's my waypoint drawing. Alright? Does that make sense to everybody? Yeah. So then the waypoint following is just this bit of code here. Okay? So So just this bit of code here is for my simple waypoint following. So what I do is I get the distance to the waypoint, right? The distance from my current position to the waypoint. I check to see the distance is less than some small number. In this case, I picked a number 0.1. And if the waypoints are less than if I get to the waypoint, in other words, like if my distance is a very small number, I advance to the next waypoint. So the advance to the next waypoint, I go current waypoint plus 1, and then I modulus it with waypoints.count as well. So that's the way of saying, if the current waypoint is, you know, one too many, then I just bring it back again to make it at waypoint 0. So that's how I make my waypoints loop, all right? And then this is the code here just to get it to move in the direction and to get it to point, right? So you call look at first of all, and that makes the transform rotate. You know, it'll change the forward vector so that the object is now pointing towards this point, the waypoint that I want to go. So this will instantly, you know, rotate the object to that rotation, and then transform.translate, you remember, always works in the local space of the object. So when you pass speed as the third parameter, this is going to move in the direction of its forward vector. That's it. Simple path following, right? The simplest possible path following that we can do. And then this is the other bit, right? If I can see, so I have some code up here to say if I can see or not. If I can see, then that means the player must be in range and inside my field of view, which is the next part of this, which we haven't done yet. Calculate the distance to the player. If the distance is greater than 5, then I just do the same thing. I move towards the player using exactly the same algorithm. So transform.lookat to rotate, to direct myself towards the player, and then transform.translate is going to move me towards the player. Is that all right with everybody? Anyone want to ask any questions on that? It's just simple path following and simple movement with what's called uniform velocity. In other words, not how things move in the real world. In the real world, things don't move like this. Really don't. You know, things don't move at a constant velocity. Things accelerate and decelerate in the real world. So the second problem then was the dot product problem, right? The can-see problem. So for the can-see problem, we have the fer de lance, which has got its forward vector like this, and we have the Cobra Mark III. And the Cobra Mark III, let's call this one B, and let's call this one A, just so we can do the diagram and do the maths, right? So the field of view calculation, I know that A, which is the fer de lance, has got this field of view, and I know that it's 45 degrees is the field of view. Did we say 45 degrees either side, or is it 45 degrees in total? I don't think I said.
Yeah, I don't think it's specified. I think mine works with the assumption that it's 45 degrees either side.
Yeah, sure. So we need to decide whether it's 45 degrees either side or 45 degrees in total. So for this one, let's say it's 45 degrees either side. How would I make it so it's 45 degrees in total?
You'd use, I suppose, 19 instead.
Yeah, so you just take 45 and divide it by 2, and that gives you the angle either side of the forward vector. So what I'm looking to find is I need to calculate this angle here. And I need to see if that angle is less than 45 degrees. If it's less than 45 degrees, then that means it's inside the field of view. If it's greater than 45 degrees, it means it's outside the field of view. Does that make sense? So how do I calculate that angle? I mean, there's lots of ways. You could do the old trigonometry way like we tried to do 2 weeks ago and ended up with just lots of code. The nice way to do it is to use the dot product, right? So, what are we dot producting with what? Well, I could take A and dot product it with B, but that would be, you know, that's a kind of a fairly standard sort of mistake that people make when they're discovering this, first of all. But A dot producted with B will just give you this angle. So in other words, a completely irrelevant angle, right? Instead, what I need to do is do the dot product of the forward vector of A and the vector which brings me from A to B. Alright, so this vector here. So the vector that brings me from A to B is B minus A. It's this vector, just this vector. And then the forward vector is, let's just call it F here. So to make this work properly, I don't think you even need to normalize, because we're not actually calculating. Oh, hang on, we are actually calculating the angle, so we do need to normalize. Yeah, you would need to normalize. For calculating, if you just want to do in front of or behind and you don't want to bother with the inverse cosine, you don't need to normalize. Just the sign is all that really matters, right? But if you're actually calculating the angle, then you need to do normalize. So we take this divided by the length of this, so that's B minus A, over the length of B minus A. This is how you write the length of a vector, by the way. And this is a vector like this, and this is a vector. So we take the magnitude of this vector to normalize it, and we dot producted it with f, and then we take the whole lot of that, and we get the inverse cosine of it. So the inverse cosine of those two will give me the angle between the forward vector and the vector b minus a. Alright, and then you check that against 45 degrees. If that angle is less than 45 degrees, you're inside the field of view. If it's greater than 45 degrees, you're outside the field of view. And that's how you do the field of view calculation using vectors. Is that okay with everybody? Remember just that simple rule, you know, and if you learn this off by heart, the angle theta is equals to the inverse cosine of, let's call these something different, p dot q over the length of p times the length of q. So just remember that off, and that's how you calculate the angle between two vectors. Okay, so that's pretty much how we'll do it. Let's code this up really quickly, and we'll go on and do some physics. That thing is videoing. There's a light on the screen. Yeah. Cool. Okay, so let's do the physics, right? The physics is the can see thing. All right, so let's see how we'll do this here. Okay, so there's two aspects of this. Maybe there's the distance part first of all. Let's see if the person is in range, okay? So let's go float distance is going to be equals to vector 3 dot distance transform dot position, and did I call it player? Yeah, player dot transform dot position. Yeah, you know what? We're going to end up calculating the distance twice using this approach. So maybe we'll just write this first of all, and then see if we can write it slightly nicer without having to calculate the distance twice, okay? So then we check to see if the distance is less than the range. Did I call it range? Yeah. If the distance is less than the range, then I know that those guys are in range of each other. So now maybe we can do the dot product bit, okay? So let's call this vector 3 2-player. And let's go 2-player is going to be equals to player dot transform dot position minus transform dot position. Okay, so that's the vector that brings me from me to the player. So that's my vector to the player. So then we can go 2-player dot normalize. Can you see what the problem is? It's not a major problem. It would bug me slightly to write it like this because I've just spent quite a long time trying to optimize the fish. Never mind, we'll crack on with this, okay? There's a very small problem here that we might think about, you know, writing in a slightly different way. There's my 2-player vector, okay? So then let's go to separate this out into different stages. The dot bit is going to be equals to vector 3 dot dot. So I'm going to be taking the dot product between my forward vector transform dot forward and my 2-player vector. And then let's go float theta. So theta then is going to be equals to math dot acos. So we use the inverse cosine of the dot product of those two vectors. Now we don't need to divide by the lengths because the forward vector is always normalized. Unity takes care of keeping that always normalized for you. So even if it goes out of normalized range, the next time, you know, at the end of the update method, Unity will renormalize that vector for us and keep it always normalized. So then, let's calculate this in degrees, right? Multiply by math f dot rad to degrees, and that will convert it to degrees. And then you can go, if theta is less than the field of view, can see is equals to true. So that means I can see. And we'll put a few we'll put some debugging stuff here so we can see what's actually happening. So let's go void manager, or it's just called manager, isn't it? Game manager dot print message. So I'm in range if I'm in the range, and then if I'm inside the field of view, let's print the message we're inside the field of view. Okay, so there we go. I'm in range inside the field of view. Let's try and see does it work now. Actually, let's make sure it compiles first. It doesn't compile. Okay, it doesn't compile because I'm already using a variable called dist. Let's call this dist to player. So now we should be okay. I think we're probably going to be in range even at the start. No, I'm not in range. Okay, so I should be able to. But yeah, I physically simulated this guy, so he's a bit flaky at the moment. In range, you can kind of see it flopping up there. I should really slow the other guy down. Anyway, if I leave it for a second, you'll see that it in fact works. So now there I am. I'll come in range. I must have changed the range to be some small number. I have changed the range to be a small number. Let's modify the range. Here's, oh, I'm on the wrong script anyway. Guard script is the one that should be on. And the range, I had 5. Let's make the range 15 instead. Okay, and there's the guard script on. Whoa! That ain't supposed to happen. Follow the path. Maybe I changed the speed too high. What do I say my speed is? 0.5. Guard is turned on. Physics guard is turned off. Okay. Ain't happening first. Let's have another look. Okay, let's make sure we're on the right script. This is the guard script. Let me just comment this code out here to make sure it's nothing to do with this code. Let's leave the path following on. Just make sure the path following is the problem. Yep, path following is the problem. Okay, a good case study. Take a look at my path following code and tell me what's wrong.
Could you zoom in a bit?
Sure.
Sorry.
Any ideas? Looks okay, it's not.
I have the same problem in the lab, and I'm trying to remember what happened, but I can't.
The distance is greater than 5, the distance is less than 0.1. Distance equals that. If the distance is greater than 5, I'm going to look at player and I'm going to translate towards the player. Let me comment this bit out here. Let me comment anything else just to make sure that I'm doing the path following code. Figure it out. Gold star for whoever can figure it out.
Is it the issue that I had where the distance to the waypoint position is too small?
No, I don't think so. Because we're just doing movement with uniform velocity, so you can use quite small values. Regardless, like even if I say I make that 1, maybe it's not the speed value. Is the speed value getting? Oh, it's probably the speed value. Because, yeah, great. Yeah, it's the speed value, okay? Look, here's a good bug, right? I suppose not a bug, but a gotcha, right? Say I decide to come in here and modify the speed value to 0.1. Okay? Let's rebuild, zoom out, jump back into Unity. Oh my god, the speed value is not updating. Unity is broke. Let's just give up programming and go study something else.
Culinary arts.
Culinary arts. Yeah, nothing wrong with culinary arts. Plenty of money in food. What have I done wrong? How do we get rid of these problems? Why is it not taking that variable? I changed the variable value, why is it not doing it?
It's because
Huh?
it's in Unity to something
Yes,
else.
exactly. Okay, so the reason why that didn't work is because when you change a value in the code like that, what that is that's the default value for that variable when Unity loads up an instance of that game object, right? So the problem is it's getting overridden by this value for speed here. What Unity will do is instantiate that object and apply this value that you have set in the UI. So I had set it to 2 here. Let's change it back again to 0.2. Okay, and let's try now. Let's say make it 0.5, I think is what I had it. Hopefully now it will work. Okay. Yeah, that's an interesting problem there, right? That's the problem. Why is this happening?
It's missing the waypoint?
It's missing the waypoint. Yeah, 0.5 is too big to get it to be within 0.1. One frame, it's this side of the waypoint. It then advances it. Next frame, it's the other side of the waypoint. So that's why we're getting that behavior. So the easiest thing to do there is either reduce the speed. What did I have the speed to, set to initially?
0.5.
Was it 0.5? It seems to be happening. It seems to be going really fast there. Nevertheless, we'll jump back into guard and we can basically change this epsilon value here, make it less than if the distance is less than 1, okay? And that gives it a gap of 1, so it doesn't have to get even close to it. If it even gets within 1 unit of it, there we go. And now it's following the path, okay? It's following the path just a little bit fast, but that's
Why not
okay.
distance is less than speed?
What's that?
Why not distance is less than or equal to speed? Doesn't that work?
Yeah, it would probably work, yeah. It would probably work for this kind of simple movement, you know? But this kind of simple movement, we probably won't stick with it for too long. It's not very nice movement. The big problem with this movement here is you can see like it just goes, instantly turns from one waypoint to the next, you know? We want to try and make it smoothly turn from one waypoint to the next. And in order to do that, we need to kind of advance on to the next kind of bit of stuff that we need to learn. So, can I pause this program now? Does everybody help you enough with how to do the waypoint following, field of view using the dot products and stuff? I'll put the code up, right? Yeah, code is up, right? And there's a class in the Git repository now, the guard class is in the Git repository, so you can take a look at it back if you want. Almost certainly there'll be a question on vector.product. Rather interestingly, there's another way of multiplying vectors which is really, really cool. But it's hard to think of a simple example for it. You know, we'll certainly, when we come to quaternions, we'll look at what's called a cross product of two vectors. Cross product of two vectors will give you a vector which is mutually perpendicular to the two vectors. But we'll do that when we're doing quaternions, right? I'll pause this and we'll start talking about physics. We'll see how things move in the real world. Okay, let me start by asking you a simple couple of questions, just to seed our brains for this one, right? The distance from Dublin to Galway, what is it? Anyone have any ideas? Ask Google. Okay, Google. Okay, Google. What's the distance from Dublin to Galway? Okay, 208 kilometers, right?
Whoa, that didn't work.
Recognize your voice.
Okay, 208 kilometers.
Even for his boots now, he's got a gold star.
Huh? Let's say that I'm driving a fairly slowish car and I want to travel at 80 kilometers per hour. How long will it take me to get to Galway?
Depends on the traffic.
Be pulled over by the guards in front.
Let's say that's my average speed, so that's my average speed.
So about 2 hours.
How'd you work that out?
4 hours, maybe?
208, what about you?
Okay, very interesting. So, if we were to put numbers on these things and we call this, let's call this X for position, and let's call this S for speed. We've discovered a relationship between the speed you're traveling and the distance that you're traveling and the time it takes. How do we write that as a little equation?
Wait.
Let's say I want to write it with X on one side. The distance travelled is going to be equals to, or in fact we'll write the one we just wrote, which is basically the time taken is equals to
time taken is equal to
Distance
the
over
distance
speed.
over the speed.
It's equals to the distance over the speed. Okay, there's equation of motion number one, right? We've already used this. This is how we do our movement with uniform velocity code. We just write it in a slightly different way. Really got x, I should probably put this symbol in front of it. You know what that symbol is? What does it mean? It means the change in x, yeah, or the delta x. The same with time. Should really be delta t, because it tells you how long it's taken. Speed is not a delta anything. Speed is just speed. Okay? So delta t equals delta x over s. Now, let's try and write this a slightly different way. Let's try and write it in a way which is maybe more gamesy. Let's say that I'm traveling at 80 kilometers per hour and I discover it takes me 3 hours to get to Galway. How long, what's the distance to Galway? How would I discover that? Now, this probably isn't going to work out, but nevertheless, you get the principle. So I'm traveling at 80 kilometers per hour, and I discover it takes me 3 hours to get to Galway. So what does that mean the distance to Galway would be? Or maybe let's say not say Galway, because this isn't going to work for Galway.
240 kilometers.
So I take the speed multiplied by time to calculate what? The distance traveled, okay? So you end up with this value here. Delta x is equals to s times delta t. Maybe we should change s and call it v, because I usually use v for velocity, right? So delta x is equals to the velocity times the time delta. Cool. All right, that's our first equation of motion. Is there anything else we need to say about it? You can see that, of course, you can rearrange these equations any way you like, just by multiplying them. If you need to calculate the velocity, so we'll do the third way, Say I travel the distance of 208 kilometers. And this time my distance of 208 kilometers took 3 hours. What's my average speed? How would I calculate my average speed?
208 over 3.
Yeah, 208 over 3 gives it the speed. Alright, so again, we can take these equations and rewrite them any way we like, okay? So if you want to get delta t, so we start off with like delta t equals delta x over v, right? Delta t equals delta x over v. Let's get v on one side and everything else on the other side. To get v on one side and everything else on the other side, what would we do here? Just to do a bit of algebraic simplification. Instead of working these out from intuitions, right?
Divide by delta x?
Yeah, I would tend to do it in 2 steps because I'm not very good at maths, right? I would multiply both sides by v, and you get v times delta t is equals to delta x, right? And then you end up with v delta x over delta t. Delta x over delta t. And again, that's kind of very intuitive, right? Your velocity is the distance traveled over the time taken. Okay? So then, that's one way to do it. And then, so we've got velocity, we've got time on this. So now maybe let's get it with the distance traveled on one side. So we'll start again here. We've got these sides. I've been going to multiply both sides by delta x. So you end up with delta x, delta t is equals to v. Delta x, delta t. So I'm multiplying both sides. Multiplying both sides by delta v. Sorry, that's not right. We start with delta t is equals to delta x times v. And I want to get delta x on one side, so what I'm going to do here, I'll multiply both sides by v. That's simple as that, right? No, hang on. Get delta x on one side there. Very simple. Delta t over v is equals to delta x. So you just take the v over and divide by. Sorry, it's Friday evening, so forgive my stupidity, right? It's the same thing. It's the same 3 equations that we all intuitively know how things move in the real world, and we knew how to calculate these things, right? The most important one of these, I think, is to calculate this one. Delta x is equals to the velocity times the time delta. Does that make 100% intuitive sense to everybody? This is how cars move, it's how bullets move in computer games, it's how everything moves, right? You can calculate the distance traveled by taking the speed multiplied by the time, and that gives you the distance. Happy? Awesome. Okay, that's our first equation. By the way, some physics books would often refer to these as derivatives, right? They would say that speed is the derivative of position. In other words, it's how position changes with respect to time. Position changes, based on the speed of the object. Does that make sense? So, yeah, okay, that's the first derivative, okay? The second derivative describes how speed changes with respect to time, okay? Let's think of a little example. Let's say at the start of some experience, my car is traveling at 3 meters per second, and then after 3 seconds it's traveling at 5 meters per second. What is the rate of acceleration? And then we need to decide, okay, say after 2 seconds. So it starts traveling at 3 meters per second, after 2 seconds it's traveling at 5 meters per second. The rate of acceleration, what's that? 1 meter per second per second. So 1 meter per second is speed, okay? And then you're saying that speed changes every second. So it's 1 meter per second is how the speed is. 1 meter per second is how speed changes. Does that make sense to everybody? So this value, which describes how speed changes, is called acceleration. So acceleration describes how speed changes, right? And we can, work out this value from acceleration as well. Acceleration, we've decided, is equals to the change in speed, which I call delta v, because we use velocity, okay, instead of speed, over the change in time. Right, that gives you the rate of acceleration. If your car is traveling at 3 meters per second after 2 seconds, 5 meters per second, the rate of acceleration is going to be the change in velocity from 3 to 5, which is 2, and then you divide by 2, and that tells you the rate of acceleration. Again, just thinking about our units of measurement here, right? The unit of measurement for position. What's the unit of measurement for position? How do we measure positions? What's the unit of measurement for position? Yeah.
A vector 3.
That's maybe what we're going to use to represent it, but what's its unit? How do we measure positions in the real world?
Relative to something else.
What's that?
Relative to something else.
Sure, yeah. So we'd say relative to the origin, relative to some origin. How would I measure positions?
Magnitude and direction.
Magnitude and direction is a vector way. That's one of the polar system.
Meters.
Just Cartesian coordinates. What's the unit? You said it?
Meters.
Meters. Okay, so the unit of measurement for position is meters. We talk about something being 5 meters away or 10 meters away, okay? From something. The unit of measurement for velocity is meters per second. And then the unit of measurement for acceleration is meters per second per second. Okay, so we've got a couple of equations here. Let's see if we can draw a little graph of how these things change with respect to time. Okay, let's say that we have something that is accelerating at a uniform rate of acceleration. If the rate of acceleration is non-uniform, this becomes a little bit more complicated to calculate. You have to use integration under the curve. Let's say we have a car, and our car is starting from rest. Okay, so the car initial velocity is going to be 0 meters per second. We'll say it accelerates at a rate of 2 meters per second per second. Okay, and let's plot a little graph of its velocity relative to its time, right? So here's time going along this axis here. And let's say you start out at time 0, time 1, time 2, time 3, time 4, time 5, and so on. Okay, up this axis here, we have the velocity. So this is time. And over here we have the velocity or speed. So we have 0, 1, 2, 3, 4, 5, 6. Okay, at time t0, the velocity is here. At time t1, where's the velocity?
2.
Yeah, it would be 2. So at time t1, the velocity has come to here. And then at time t1, or at time t2, the velocity is going to be 4. Okay, so I go 2, 3, 4. And then at time 3, we'll be up as far as 6 meters per second. So this is the graph that shows you the relationship between very badly and badly drawn and all the rest of it. This is the relationship between time and speed and acceleration drawn in a graph. Does everybody see that? So as the time is accelerating, or as the speed is accelerating, time is increasing, and the slope of this line becomes, gets higher. Okay, so the line is going higher up from left to right. Okay, so we end up with this little equation here. So interestingly, what's the equation for that line? What's the equation for any line? Do you remember, how do you calculate the y value for a point on the line given certain input values? How do you calculate the equation for a line? You remember this, I'm sure, from cast your minds back. It's the good old days, healthy and happy days.
Y over it.
Huh?
Y over it.
It'll be delta y over delta x gives you a number which is called the
Slope.
slope. Yep. So y is going to be equals to the slope multiplied by x plus
C.
c, which is the
Just an offset, basically.
is the intercept. It's actually where it intersects with the y-axis, right? So we have this equation called y equals mx plus c. And let's see if we can write this. What's y in this? What's y in this diagram here?
Velocity.
It's velocity. Okay. What's m?
Slope.
It is the slope, but in terms of this, what's m?
Oh, the acceleration.
The acceleration. Sure thing. How would I calculate the acceleration? Like again, think back to this, right? How did we calculate the rate of acceleration here? We took this one minus this one over the change here. Do you remember how to calculate the slope of a line? It's y2 minus y1 over x2 minus x1. So it's the change in y for every change in x. And it's the same equation here, right? So we take this value called m, which we said is acceleration. But up here we discovered that acceleration was equals to v2 minus v1 over t2 minus t1. So it's the ending velocity minus the starting velocity divided by the ending time minus the starting time. And this is the same thing we're doing here. You know, this is a. If I was to write this in terms of the slope of the line, we'd end up with y2 minus y1 over x2 minus x1. Okay? So we have a times t plus the starting one, which is going to be v0. My starting velocity. So that's the relationship between the line and the acceleration with uniform velocity. Is that okay with everybody? You can see all of that? Alright. The simple case, when I'm not accelerating, I just take the speed that I'm travelling and I multiply it by the time that I'm travelling for, and that gives me the distance travelled. Is that fair enough with everybody? Take the speed multiplied by the time gives you distance. In this example here, it's slightly more complicated because, let's imagine like I have this area here, and I want to calculate the distance travelled. I want to calculate the delta x value given this sort of input, right? If I was travelling at a uniform velocity, we'll say I was travelling at a uniform velocity across here, then I would just take the velocity, which is this one here, and I'd multiply it by the time. So you can see it's the same as the area under this little rectangle, isn't it? Can everybody see that? If I was not accelerating, I just take the velocity, multiplied by the time, same as the little rectangle in here, and I would end up calculating the distance travelled. Right? So it's the same as the little rectangle in here. When I'm accelerating with uniform velocity, though, it's actually a slightly more interesting calculation, because what it is if I want to calculate the distance travelled, we'll say from here to here, just this time, time t1 as far as time t2, you can see that it's in fact this area under here, plus this area up here. And this will tell you how far you've travelled if you're accelerating. Fair enough? Could you guys write an equation to figure that out? Okay, I'll put some numbers on it and I'll let you see if you can write an equation for it. If you can derive the equation for it, right? Let me put some numbers in here, okay? Let's call this one v1. This is the starting velocity. Let's call this one v2, the ending velocity. And then this is t1 and t2. Alright, if you want it, you can call that delta t. If you want, you can call this delta v. Okay, so take 5 minutes, get a page out and see if you can derive the equation for how far I would travel if I was traveling with uniform acceleration. I shall pause the video at this point so we don't have a silent moment on the video. Okay, so we know that it's this area under the line here, okay, and there's two aspects to this, right? Calculate this rectangle and then add half of this rectangle up here, and then you'll be able to calculate the distance travelled based on uniform velocity. Right, so let's try our uniform acceleration. So let's rub some of this stuff out here. Okay, so we have this value here, which is delta t. So I can take delta t times delta v, which is delta t times v0, or v1 I call it, right? v1 is what I call it. That gives me that area under here. So this delta t is the change in time multiplied by the starting velocity. And that's going to give me this initial velocity. This area up here is going to be equals to a half delta t as well. Delta t times the change in velocity, which is delta v. Okay, the change in velocity. And that's your kind of equation. But we can write it slightly nicer. In fact, it's usually written as a slightly nicer equation, because delta v, we remembered, the change in velocity is also acceleration times the time delta. And that makes total sense. You know, that's how we calculate acceleration. That's how we calculate the change in velocity as well, based on acceleration. The change in velocity is the amount of acceleration multiplied by the time that you're accelerating for. Yeah? We discovered that. So we can rewrite this then as delta t times v1 plus a half a times delta t squared. Yeah, because we go delta t, a, delta t, and then you go a delta t squared. What do you reckon, everybody? You buy it? Do you agree? I didn't invent this, by the way. Who invented all of this stuff? Who came up with all these equations? Was it Steve Jobs? No, I don't think so. Was it Google? Was it Sergey Brin? Or was it, what's the CEO of Microsoft called? Satya Nadella. Yeah, okay, none of those guys. Who invented all this stuff? Gold star for whoever tell me who invented all this stuff.
Faraday.
Who?
Faraday.
No, further. Isaac Newton. He discovered all of this stuff. Remember the guy with the apple on his head? Okay. Let's try a problem, okay? Let's imagine, because you have to imagine this one, right? It doesn't actually work in the real world. We have to imagine that there's no atmosphere, because when there's atmosphere, things change just slightly, right? The height of the Empire State Building. Let's find this out. I have to Google. Okay, Google. What's the height of the Empire State Building?
381 meters.
Okay. So the height of the Empire State Building is 381 meters.
That seems really short.
Tell me, how long would it take if I dropped a coin from the top of the Empire State Building? How long would it take for the coin to reach the bottom? And how fast would it be traveling when it reached the bottom? Now you have to imagine that this is in a vacuum, because there's another thing happening in the real world, which is friction. You know, so what will happen is it will reach a certain speed, and the force of friction due to it, the coin colliding with the air, as it's the air particles that's going down, will cause it to slow down. And it reaches what's called terminal velocity. In other words, it will go so fast and accelerate, and then it won't accelerate anymore, because the counteracting force from the friction stops it from accelerating further. So for this simple example, let's imagine that it is in in no atmosphere. No atmosphere. Okay? Oh yeah. The one other thing you need to know from this little one is what is acceleration due to the force of gravity? And that's a really interesting challenge, isn't it? Because as we know, in the real world, heavy things fall faster than light things, don't they? Let's do a little experiment. You know, if you take something really heavy, it's only a coin, you know, so it's probably going to fall slower than if it was a rock. Yeah? A rock will fall a lot faster than the coin because the rock is heavier. The rock has to fall faster because it's heavier. Isn't that right? No? Of course, it's obvious. It has to be. Let's do a little experiment, right? Let's take this, which is a light thing, and let's take this, which is a slightly heavier thing, and we'll do a little experiment. We'll drop them, and of course, this is going to fall first, isn't it? Definitely. Yeah, we know it's going to happen. It has to be true. It's obvious. It's very intuitive that fast things fall. You know, the faster things, the heavier things are going to fall faster. Let's try it. Everybody ready? Watch very carefully.
Can't see.
1, 2, 3. They fell almost. No, okay, like that was just, you know, a mistake. Obviously they don't fall at the same speed, you know, that was just, something weird must have happened there, you know, like a time-space anomaly or something. We'll try it again. This time definitely this one's going to fall faster. I'm dropping them from the same height. 3, 2, 1. No, again. Oh my god. They both landed at exactly the same time. Ah, my head.
No, Isaac, you prick.
What have we discovered? What have we discovered?
Gravity.
Huh? What have we discovered by doing this little science experiment? Yep, acceleration due to the force of gravity is a constant regardless of the mass of an object, right? In actual fact, it's very simple when you think about it, right? There's one other equation which we haven't done, and we'll do it after the break, right? But it will explain why everything falls at the same speed. So, acceleration due to the force of gravity is 9.81 meters per second. So everything on Earth accelerates at a rate of 9.81 meters per second. Okay? The height is 381 meters. From those two numbers, and using the equations that we've already worked out, you should be able to calculate those two things. How long it's going to take, what speed it will be traveling when it reaches the ground. Okay? Get to work, everybody.
Isn't there a net on the net first aid building?
Huh?
Is there like some kind of
Yeah.
net?
Solve this little bit of physics first of all. Okay. So, this is the equation that we're going to use to solve this problem here. So we have delta t times v1. What's v1? Initial velocity, which is 0. So immediately we scrub that bit off there. And we end up with a half a delta t squared is equals to 381. A we know is 9.8, so you end up with a half times 9.81. Delta t squared is equals to 381. So our final sort of equation looks like delta t is equals to 381 divided by a half multiplied by 9.81, and that's squared. So you end up finally with delta t is equals to the square root of all of this stuff together, 381 divided by a half multiplied by 9.81. I think that's correct. Is that okay with everybody? Does that make sense? So delta t is going to end up as being 381 over a half multiplied by the rate of acceleration, which is 9.81. You get the square root of it. So you do all of that, and you end up getting a value of, what was it, 8.81 seconds? Was that what we got? Yeah. So you end up with delta t is equals to 8.81 seconds. And then to calculate the final speed, we can use this equation here. Final velocity is equal to the rate of acceleration multiplied by the time delta. So the rate of acceleration is 9.81 meters, and then we are accelerating for 8.81 seconds. So you multiply one by the other, and we get, what did we get, 86?
86.46.
So 86.46 meters per second, and our final speed is going to be 8.81 seconds. All right, so we have a whole pile of equations now, right? I think it's time that we actually did something with them in Unity, because otherwise all of this is just abstract. You know, it's all like what do you call this, applied maths, without any relationship to games. Before we go and write it in Unity again, let's just... Should we write it in Unity? No, let's not write it in Unity. I said we won't write any Unity until we've done all of the maths first. Let's do the one last bit of maths. The one last bit of maths is really, really easy, okay? We'll write up all the maths that we have so far, all the useful equations. And then we'll do the one last equation, and then we'll do something. Equation number 1 is to calculate the change in position. So delta x is going to be equals to velocity times delta t. Okay, change in position is equal to velocity times the amount of time I'm traveling for. Equation number 2 we discovered was delta V is equals to the rate of acceleration times the time delta. Okay, and you could write that as V2 is equals to V1 plus acceleration times the time delta. All right, it's another way to write the same thing. In other words, the new rate of velocity is equals to the old rate of velocity plus the amount of acceleration multiplied by how long I'm accelerating for. When you think about that, it's intuitively, it makes a lot of sense as well, right? If I'm traveling at a velocity, put my foot on the accelerator for 2 seconds, my new velocity is going to be equals to the old velocity plus the rate of acceleration multiplied by 2. Does that make sense for everybody? There's equation number 2. Equation number 3, which we probably are not going to use, to be perfectly honest, but it's just useful for bringing everything together, is this one. Delta x, which is the change in position, when we have an acceleration, is equals to a half the rate of acceleration delta t, half a, what is the equation again? Half delta t times v1,
Delta t v1.
delta t v1 plus a half a delta t squared. So that's our third equation. Okay, back to what I maybe mentioned earlier, we said that velocity is what's called the first derivative of position. Acceleration is the first derivative of velocity. So then what's the derivative of acceleration? In other words, or what causes acceleration? So what causes an object to accelerate? Force. This other thing that we haven't really talked about. Force. The interesting thing about force is considered to be applied in a moment of time. So there's no time quantity associated with force. You can apply force for a duration, and then that's going to cause, lots of acceleration. But force causes the change in velocity, in other words, acceleration. But the velocity will continue even if the force is taken off. And you imagine that, like, think of the spaceship in a vacuum. Spaceship in a vacuum. I should have went and got my spaceships. I knew I should. Can't do a game engines class without spaceships. So, you imagine a spaceship flying through space, you turn the thrusters on, the spaceship accelerates off, you turn the thrusters off, the spaceship doesn't stop, it keeps going forever. On Earth, of course, things stop because there's friction all around us, right? But in a vacuum, things will continue to move indefinitely, so long as no other force causes them to decelerate.
Isn't force just kind of the same as acceleration? Like, well, sort of. I mean, there's F equals ma. So.
Yeah, that's where we're kind of going with this, yeah.
But that doesn't mean that force is the derivative of acceleration. It means that it's acceleration divided by mass.
Sure. Maybe derivative is not really the mathematical term. It's something that causes acceleration. It's one level above it. It's the third of the 3 equations, what's called an Euler integration function. But here's an interesting thing about force, okay? Force is definitely dependent on something else, right? Let's look at force, for example, right? Let's see if I apply some force to this, what will happen, right? It goes. Everybody see that? It's moved. Let's try and apply the same force to something else, right? What happened?
Hurt your finger.
If you don't believe me, try it yourself. Try picking a light object and flicking it, and then try picking a heavy object and flick it, and see what happens. There you go. Yeah. So what kind of acceleration does force cause? Or what does the acceleration also depend on? Depends on the mass of the object. Okay, so you can apply the same force to a light object and it will cause a lot of acceleration. If you apply the same force to a heavy object, it will cause a small amount of acceleration. Alright, so that relationship is actually really easy. The force is equal to the mass times the acceleration. This is a rather useless way to write this equation. I think it's much easier to just rewrite this in terms of acceleration. And it's very intuitive. Acceleration is equal to the force over the mass. Alright, so the amount of acceleration that is due from a force is proportional to the mass of the object. Heavy objects will cause a small amount of acceleration, and then lighter objects will cause more acceleration. How is it possible then that big objects accelerate at the same speed as small objects on Earth. What does that mean? It means the force of gravity.
It's constant.
The force of gravity, it is constant, but why is it possible that, why is it that the force of gravity on a big object causes the same acceleration as the force of gravity on a small object?
Because gravity also uses the mass of the object.
Exactly. So the force is proportionate to the mass of the object. Big, heavy objects are more affected by the force of gravity than small objects. And in fact, it all evens out so that the force of gravity, at least on Earth, is a constant, or as close as possible to a constant for us to be able to do simulations and approximate things with a constant gravity force, right? A big, heavy planet has got lots of gravity acting on it. A tiny individual particle only has a small amount of gravity acting on it, right? So the force that's acting on these objects is bigger or smaller depending on the size of the object. Consequently, the acceleration is a constant due to the force of gravity. And this is our third equation, right? So we end up with these three equations, right? Acceleration equals the force over the mass. Velocity, or the change in velocity, is equal to the acceleration times the time delta. And then the change in position, delta x, is equal to the velocity times the time delta. They're the three most important equations of motion that you can use to do simple, what is called particle physics, right? P-A-R-T-I-C-L-E physics. Alrighty, once we do particle physics, you can fake things like rotations in particle physics, which we'll do. But for now, I think, yeah, it's kind of time to write some unity. What do you reckon? It's getting towards that time on Friday. Right, let's write some unity. Okay. So, what we'll do, first of all, if you fire, your project that we worked on the last day, let's do a few things to it. Let's pick the Cobra Mark III, and instead of doing the movement using the simple movement that we were doing, in other words, always moving in the direction of our forward vector and stuff, let's try and push it around using forces instead, okay? So let's pick the Cobra Mark III, and let's attach a script to it. I've already added a component called a pusher. I'm going to add another component here, because we'll write it again from scratch, right? Physics. Let's write a script called physics movement, okay? And this is not using the physics engine, but this is just writing our own physics based on these simple equations that we had. Okay, so there's physics movement. So let's now go and edit this in Visual Studio. And let's add some things. Okay, so here's my physics movement script, right? We're going to write a simple script here. We'll make a couple of variations on this. We'll make a simple script, and all it's going to do is push the object in a different direction depending on which keys are pressed, right? So let's kind of set this up. We might as well put a few things in here. Let's put in the key codes, right? Key code for the left key is going to be equals to, we'll put some default values in here. Public key code left is going to be equals to key code dot, sure, why don't we use the left key here? Oh no, we can't use the left key. Oh, we can use the left key. Oh, we're not using it. Left arrow. Alright? We'll do the same for right, and we'll do the same for forward. So the right arrow, let's do forward. Key code dot up arrow. And let's do backwards for key code dot down arrow. Okay, cool. Sorry, let's do backwards, right? Okay, so there's my keys. Next thing I need to do, and in fact this is really the kind of the big learning outcome of this, let's add some state to this object that we can use to implement this physics equations that we just did. What do we need to add? There's a couple of extra variables that the thing's going to need to add. What would we need to add? We have position from the transform. What extra fields would we need to add, would you think?
Velocity, yeah.
Yeah, let's add velocity, okay? What type will velocity be?
Vector 3.
A vector 3. Why a vector 3 and not a scalar? Why not a float?
Because
It has...
Because it's going to represent the fact that it might be moving.
Exactly. All right. This is why we call it velocity rather than speed, because velocity is a three-dimensional thing, right? Because velocity can be from all different directions. So it's a directional thing. So we'll use a vector for it, right? Public vector 3. So let's make it a vector 3 velocity. Anything else?
Velocity, acceleration.
Yeah, if I was to tell you that we're not going to make acceleration here, we're going to make it somewhere else, what would you think about that?
Be offended.
I'll tell you why we won't make it here, because as a rule of thumb in programming, should we try and make our variables fields, or global variables, or local variables? What's the preference? Always.
Local variable.
What's that?
Local?
Local. The preference is always to try and make things local. The acceleration is something which is just calculated based on the force and then thrown away. So it's not something that this object needs to maintain about itself from one frame to the next. So we might make that a local variable. Anything else? Force, I think I would be inclined to make a global variable, because potentially lots of methods might want to add force to the object, okay? For now, it kind of makes sense. In fact, you know, it doesn't really matter. We can make acceleration public as well, but I think it sort of makes more sense to me that we make this local. Velocity, force. Okay, let's make another scalar. And let's call this thrust. Public float, thrust. And this is going to be the amount of force that we're going to apply to this object when I press the keys. Interesting thing I forgot to mention, what's the unit of measurement for force? Anybody know? Newtons. Okay, so newtons is what's called the unit of measurement for force. Alright, so thrust is going to be in newtons. What did I use for my thrust? For the hell of it, let's put 10.0 F. Okay, 10 will do for now. Alright, so there's velocity, force, thrust. In the update method, I am going to do some calculations with these and implement those physics equations. First equation, first thing we're going to do is we're going to now add some values to the force depending on which keys are pressed, right? So let's go if input dot, is it input dot key down or any key or get key, or what's the method? Can you guys remember from last week? Get key. Is it get key?
I think it's...
Yeah, I think it's get key. Huh?
Yeah, you can get key down.
Okay, if input dot get key, you don't want that semicolon there. If the forward key is pressed, then I want to add some force. Okay, so we're going to go force plus equals to. Next question, which direction do we want to apply the force? If I press the forward key, it should be in the... How would I calculate the direction and the vector that I want to add for force?
Vector 3 dot forward.
Very good. Not vector 3 dot forward.
Transform.
Transform dot forward. Okay? So in other words, when I press the forward key, the force I want to apply is in the direction of the object's forward vector. You know what I mean? So transform dot forward, and then we'll multiply it by the thrust. Okay, so this is going to apply 10 newtons of force in the direction of the forward vector. Okay, let's do the other keys then. If input dot get key, the backwards key, we'll do our force in the opposite direction, right? Let's do force minus equals to transform dot forward multiplied by the thrust. We'll do our left and right keys. We'll end up when we do this, by the way, with not getting very realistic thrusting movement, because double entendres there. What we'll end up getting is we'll end up getting something which doesn't rotate very naturally. And the reason why is because, of course, in the real world, there's a whole bunch of equations that govern how things rotate, and we haven't done those yet. Okay. So if input.getKey left, I press the left key. Force plus equals to, so the left key should be minus equals to transform dot left. There is no transform dot left, it's transform dot right. So it should be minus equals to transform dot right multiplied by the thrust amount. Okay? And then we'll do the last one, which is the right key. Force plus equals to that. Okay. So this is what's called a force accumulator. This force is all accumulating up. Depending on which keys are pressed, I'm adding some values to the force. Okay? Now, let's implement these three equations. Acceleration is equals to the force over the mass. So let's calculate the rate of acceleration.
Is that not just going to move it right and left across the axis? And would we not want it to rotate?
Yeah, it kind of will rotate because, what are we going to do? You'll see in a minute, it will kind of cause it to rotate, okay? Yeah, you're right. Technically it's going to strafe, but because of the fact that I'm going to be rotating this object so that it always points in the direction of it's traveling, in other words, its velocity vector is going to be its forward vector. When I push it to the left, it'll actually cause it to turn because its forward vector is going to rotate and hence its right vector is going to rotate as well. So acceleration, we said, very simply equals to the force divided by the mass of the object, and we forgot to declare the mass. So let's come up and declare the mass. We'll give it an initial value of 1.0f. Here's a little thing, by the way. The velocity and the force are not really things that I want Unity to have access to, but I might still want to make them public so that other game components can get access to them. What you can do here is you can put this code up here, hide in inspector. It means you can have it public, but it doesn't get exposed to Unity, because these things I don't really want them to be exposed to Unity. There's no point. I can't set the velocity anyway, so maybe you can set the initial velocity, but certainly the force, probably, I don't know if it makes a lot of sense. You know, maybe it does. Maybe I want to not hide them. Anyway, it's just a little aside. Right, there's the acceleration. Now, the velocity plus equals to acceleration multiplied by time, dot delta time. And then finally, we're going to move the position in the direction of the velocity. The way I would have originally done this is gotten the position and gone position plus equals to and stuff, but it's not really the Unity way. The Unity way is to do something like, how did I do this? Let me just double check to make sure. Oh yeah, okay. I did transform.look at first of all. That's not how I did it, that's how I did it a different way. That's physics art. Okay, let me just double check this code by opening up my solution that I did earlier on and see how I did it. Oh, okay. Yeah. Okay, how I did this. This is kind of more the Unity way. I think this is kind of more the Unity way, okay? Last year I would have done it by just affecting the object's position and blah, blah, blah. I think this is more the Unity way of doing it, right? I need to check to see if my velocity is got a value. Because I can't, if my velocity is 0, I can't set the forward vector to be the velocity vector. Because then the forward vector has to be a normalized vector, okay? So we check to see if the velocity dot magnitude. And I've been planning to use this method here, square magnitude. Anyone like to hazard a guess as to why I would use square magnitude rather than magnitude? Okay, So the magnitude of a vector, what do you need to do to calculate the magnitude of a vector? You take the x squared plus the y squared, and then you get the square root. So the magnitude squared is the same as the magnitude, but you just don't calculate the square root bit. So it saves you one calculation, right? And this becomes really critical if you've got hundreds of objects moving around the scene at the same time. You don't have to calculate the square root, then don't calculate the square root. You know, so square magnitude is just the magnitude squared. In other words, it's x squared plus y squared. Sorry, if the velocity dot square magnitude is greater than some small number you can write as float dot epsilon. Float dot epsilon is the smallest interval between two floating point numbers that you can store in a 32-bit floating point number. Did we do IEEE 7.4 in second year, you guys? OOP people? Never mind. Okay, we know that floating point numbers are stored in 32 bits and they lose precision. Float.epsilon is just a very, very small number, okay? This checks to see if the velocity is not essentially zero or very close to zero. If the velocity is not very close to zero, then you go transform dot forward is equals to the velocity. A weird thing happens here. This velocity automatically gets normalized for us. Okay, Unity does that for us because, sorry, the forward vector will automatically get normalized for us. Really, what I should be doing is velocity dot normalized, but that's just one extra calculation too many. Unity will do it for us anyway. And then transform transform.translate 0, 0, velocity. No, hang on, where did I do this? Sorry, I knew how to do this last year and I just figured it out this kind of more Unity way. For sure. Oh, weird. Okay. You know what? I think the actual non-Unity way of doing it is slightly nicer. Let's come back here again. Physics movement. Okay, take a look at the last line of code there. This is, I think, a slightly more Unity way of doing it, but maybe it's not terribly Unity-ish because it's still ugly. Okay. If I just do transform.translate, it moves in the direction of the forward vector. Oh yeah, well then I could just take the magnitude of the velocity. God, it's really ugly, this way of doing things in Unity, I think. Why can't I just take position equals position plus? That's just right in the non-Unity
Position
way.
is relative to the world.
What's that?
Position is not local, it's relative to the world.
Yeah.
So you could have done position, couldn't you?
I can, yeah, definitely. Yes, Brian. Absolutely, yes, but you've got to factor it in twice. One delta time is to calculate the new velocity, and then the second delta time is to calculate the new position. I'm going to write it in a non-Unity way. This is ugly. Sorry, Unity, this is just ugly. Okay, velocity plus equals to acceleration plus pi by the time delta. Let's do the same thing with the position. Okay. Okay, there's our third equation, right? Written in a slightly more ugly, well, I don't know. I think it's just easier to understand this, right? Here we go. Yeah, look at the last bit, right? The last bit is just the third equation, right? Position, I get the position. Position plus equals to velocity multiplied by the time delta. Transform that position equals position. So that's the third equation there. Delta x equals velocity multiplied by delta. So we've implemented the third equation there. The other way to do this is by fecking around with translate in Unity, but I think this just kind of looks neater to me. Last thing we probably want to do is I want to make the transform, I probably still need that code, right? If velocity dot magnitude squared is greater than 0.0, is greater than float dot epsilon, so it's greater than some small number, then transform. There's an awful lot of signs in this room.
Friday evening.
Okay. Look. Okay. So either you can use translate, or you can use just get the position, calculate the new position, to set the position back again. This last bit here, it's the same thing. All I'm doing is I'm taking the forward vector and I'm making it so that the forward vector is the velocity. There's a big limit to this, right? This is called steering, by the way. We do a lot of steering in the second semester, calculating forces to do different types of AI. But the big limitation with this is that your object is always going to point in the direction in which it's traveling. And of course, that's not what happens in the real world. You know, you think of a car going around the corner, you know, the car's traveling like this and then it does a slide like this. So the car's moving in this way and pointing in this way. By making the forward vector equals to the velocity, it means the object is always going to point in the direction in which it's traveling. It's a little simplification and that we can do at this stage to implement steering. Let's run the program and see what happens. Okay, so here's my little spaceship over here. Let me try my arrow keys. Whoa! What the hell? Let's try one more thing. Let me see. We press the forward arrow. Whoa! What happened?
You're not resetting the force?
Yeah, you got to reset the force, right? Because what happens here is I'm adding to the force vector. The force vector then gets integrated each frame over and over and over again. It's like turning the engines on and never turning, or turning on the thrusters in your spaceship and then never turning them off again. Okay, because I set the force vector in every frame, then more force gets applied, right? So you need to remember to do this, which is to go force equals vector 3 dot 0.
You could also make it a local variable.
What's that?
You could also just make it a local variable since you're not using it anywhere else.
The force?
Yeah.
Yeah, sure, I know. The reason why I kind of do it like this is because usually I'll have a load of stuff to do, seek and arrive and whatever, so they're going to affect the force, but maybe need it as well. Yeah, maybe I didn't need to make it a global variable as well. Yeah. Anyway, so now we're resetting the force accumulator. And now my object is going to, when I press the up arrow, it will start to accelerate. You can see it accelerates up. And because there's nothing causing it to stop, it'll just continue to move at uniform velocity. And you can see when I turn it, turning is not very natural like this, you know? Because I haven't really properly implemented rotation.
Also, turning seems to be accelerating.
Yeah, definitely, because I'm applying force every time I turn it. Yeah, so this isn't how to do natural turning. This is just, you know, turning so we can use these simple equations. Next week we'll use quaternions to do the turning, and it'll be much nicer. Let's see, is there one last thing we can do today? Yeah. Quick and dirty way to modify this so that the object accelerates and then gradually slows down. Right? In the real world, what would we call that? Friction, yeah. We'll try and do friction really quick and dirty. In actual fact, friction is not that hard to do properly. There's just another set of equations for implementing friction. But one simple thing you can do is what's called damping. Okay, and there's at least two ways to implement damping. You can do it the really quick and dirty way, or you can do it the slightly more complicated way, which is to take the speed into consideration. Let's do it the really quick and dirty way. The really quick and dirty way is just to go. Everybody watching? Velocity multiplied by equals to 0.99 f.
Yeah, that's how I did it.
Yeah, that's okay, but it doesn't take the time into consideration, so it's not actually, what you'll end up happening is it'll decelerate depending on the frame rate. You know what I mean? If you have a high frame rate, you're going to get lots of deceleration. If you have a low frame rate, you'll get much less deceleration, because that is not taking the time delta into consideration, right? So if I just
multiply it by time delta?
Yeah, you would have to multiply the rate of deceleration by the time delta. But anyway, now you can see I give it a little bit of thrust, It accelerates for a little bit, and then that damping will cause it to slow down. You know, because it loses 1% of its velocity every frame, and eventually it'll slow down. How would we take time into consideration with that damping? You know what? Rather than try and do this from memory, I wrote it earlier on, and it's not too difficult, right? So this is the equation, and just make sure, I think this kind of makes a little bit of sense, right? So I have this value damping here. In this case, I actually specified the damping amount as equals to 0.1. And what, or maybe not 0.1. What did I say my damping value was here? Look, see? Okay, it is 0.1, right? What I want is, I want my velocity to be decreased by 10% every second. That's what I'm saying. Okay? So you take 1 minus the amount of damping. The damping per frame is going to be damping because it's going to be 10% in 1 second. So you take damping multiplied by the time delta. It tells you how much damping to apply this frame. And then you take 1 minus this and then multiply the velocity by this amount. And then you'll get damping, which is time dependent. Does that make sense, Shane?
I don't think that's
I don't
right.
think that's right.
Why?
Imagine if the delta time was 2, you'd be damping at minus, or...
Yeah, that's -1.
Yeah, but that'd be correct. Oh no, hang on, you're right. If the time delta was 2, you would take your damping, say my damping is...
I think what you want is exponents.
What's that?
I think what you want is exponents. You want to raise the damping to the delta time.
Raise the damping to
Damping to the power of delta time, I think is what you know.
Why?
Like, what you're doing here, if you get a delta time of 2 seconds, I should say, running really loudly, you'll end up with a damping of -1. So you'll actually just swap your velocity.
Yeah, I just worked this out like in about half an hour before the class, and I actually probably didn't put as much
It
time
probably
into it.
looks right most of the
I'll
time.
tell you what, we'll go back to the other one. Just multiply it by 0.99. That way it'll slow down, okay? I won't ask this in an exam. Okay, so these are the simple equations of motion. Do you guys feel at this stage that you could modify that program that we made last week, instead of actually using lookat and transform to get it to follow the path, instead you can calculate a force which pushes it towards a point?
Yeah, I'd say I could modify it.
You can do it? So it pushes it towards the waypoint. When it gets to the waypoint, then obviously you advance to the next waypoint. Same type of code, but basically to do force-based movement instead of movement with uniform velocity. I'll show you what it looks like, you know, and you can have a crack at it in the lab next week. This is the physics guard script. So this is a guard that's using physics rather than using plain old movement with uniform velocity, and you'll see that the movement is a little bit nicer now. And by the way, I haven't added any rotations, apart from the fact that now the rotation is, you know, it just calculates the force based on position that it needs to travel to, so it will calculate a force to push it towards a particular location in the scene. It takes a good bit of fiddling around, actually, to make this really correct. And to do it really nicely, what you have to do is you implement what's called a seek steering behavior. Instead of actually calculating the force to push it to the destination, I'll show you how it works.
Maybe we just do like 3 right.
Okay, say there's my ship A, there's my destination point B, this is my current velocity. Say I want to push A towards B. What direction would you push it?
Towards B.
Okay, so you would just push it in this direction. You just push it in that direction?
Yeah.
Well,
You-
you could also
yeah.
Could end up-
you could also push it. Well, I don't know if this is the answer, but you could also like effectively slow down, sort of like not push in this direction as much, and then be forced to apply this way.
Sure, how would you calculate that? I mean, it's not quite, you could push it in that direction, and over a period of time it would move in that direction, but how about if I pushed it in this direction instead? Would that make more sense?
Yeah.
So instead of pushing it like this way, you know, I'm traveling in this direction, I want to push it in this direction, so that over a number of frames it starts turning and it eventually ends up pointing like in this direction. So it's better to actually push it in not quite towards it, but actually even more extreme. Again, imagine I'm traveling up in this direction here. I want to move to this point over here. I could just push it in this direction constantly, but much better would be to push it in this direction. And that would cause it over a number of frames eventually to end up being in that way there. You know what I mean? So, yeah, it's better to do that.
Yeah.
So how you do that is, first of all, you calculate the B minus A. Oh, you know what, I might just let you guys figure it out in the lab. You know, you'll have a bit of fun pushing things around in different directions. Yeah, and seeing what happens. So you take, I'll let you figure it out in the lab. Let's leave it at that. It's Friday evening, okay?
I'm doing it the other way.